morning. Am I audible?
Yes.
Okay. So in continuation to our earlier discussions, we will see that how the language of computer has evolved over time. So in the last class, we have started discussing about instruction sequencing and state line sequencing. So we have understood that in a memory, how the instructions are sequenced or stored in state line sequencing. Okay. Now today we shall take some particular example of instruction set, and we see that how the instruction set looks like and how can we use them for writing assembly language programming. We start with a topic that's called instructions. Which are nothing but language of the computer. You have already started learning for 808.5 in laboratory. Also, time to time, I have given some example of RISC type of instructions. Okay. Now today we shall start one particular family of RISC processors and see that how its entire instruction set looks like. Okay. So what we are going to do, we shall first categorize these instructions and try to understand that how high-level language, high-level instructions written in any other programming languages like C or Java can be converted into these assembly instructions using a particular type. Okay. So what we will take here is an MIPS instruction code. It's a RISC processor. So whenever I say that it's a RISC processor, you must be knowing that what do I mean by RISC? Okay. Because we have already discussed it, that what is RISC processor. Now MIPS is a 32-bit RISC processor. It's a 32-bit RISC processor architecture. It has 32 registers, numbered from 0 to 31, each with 32 bits. So, to identify a register, in MIPS, we need 5 bits. We need 5 bits. Why? Because 2 to the power 30, 5 equals to 32. So uniquely identify one register in MIPS, we require 5 bits. Now, the register names are like this. When we write assembly program, names are like this. We give a symbol $, okay, and then we give the name. So 0 is a register whose register number is 0, and its usage is it stores the constant value 0. Similarly, register number V0 and V1, their number two and 3, they are used to store values for results and expression evaluation. These are all special registers. The next set of a few registers, they are called A0 to A3. So you have 4 to 7, they are used for arguments. Then there are temporary registers which are used for normal calculations, T0 to T7. So we have 8 registers, therefore temporaries. Then we have 8 registers, S0, S7, therefore saving values. Then we have again some temporary T8 to $T9. So its number is 2425. There are more temporaries. There are some more special registers like a GP is there, which is number is 28. Register number, name, and usage. It's a global pointer. Then we have stack pointer. This is number 29. This is stack. Then we have frame pointer. This is number 30. This is frame pointer. Then we have return address, RA 31. Actually, there is one register, which register number 1, which we do not, we have not mentioned here. It's used for flags. Okay. So this register is not directly accessed. So rest are like these numbers. Now we usually in our programs we do not need, frame pointer, return address, global pointer, stack pointer is also not needed from our side. Commonly, what we require to use these registers mainly. The temporary registers T0 to T7, more temporaries T8, T9, and yes, 0 sometimes may be needed for special type of calculations. Okay, arguments and other things all will be automatically used for function arguments. Okay, whenever you call subroutine, so these will be arguments will be passed through this. So if you use functions, okay, and you need to pass arguments, then these registers can be used. Okay, so these are special purpose registers. Okay. Gradually, you will know that if you use, start writing complex codes using this, you will be understanding that why these registers are needed. Okay. MIPS it's a 32-bit architecture, so it's a 32-bit architecture. So it has its own instruction format. Before I go to the instruction format, we need to first let us see that how the typical high-level languages can be converted into assembly language. Okay. So first we will look into the operations of the hardware. Operations of the hardware. So typical example is we write add ABC. I have not mentioned anything about ABC. Let's assume that. So what it does, this instructs Even though we have discussed similar thing, but it's more generalization I'm doing now. So this instructs a computer to add two variables B and C and put their sum in A. So this particular notation is rigid in a sense that MIPS arithmetic instruction performs only one operation. So this is a little bit rigid thing, that MIPS instruction for addition or similar arithmetic operation instructions, they only perform one operation at a time. And we must have exactly three variables. Exactly three variables. So you cannot actually add four variables at a time and put it into it. So if you would like to do something like that, A equals to B plus C plus D plus E. So if your objective is to do A equals to B plus C plus D plus E, we don't have an instruction to do that. If this is my high level language, MIPS is a rigid machine in terms of operations. This cannot be directly computed here. So what we will have to do? We'll have to break it. We can do something like this. Add A, B, C. We're going to add A, D, then add A, E. So what it does? This makes A equals to B plus C. This makes A equals to A plus D. This makes A equals to A plus E. Now, when these three instructions are executed in sequence, you know that finally what you get in A is B plus C plus D plus E. So in a sense, this format is rigid. We cannot have more than two operands at more than three operands at a time. And all arithmetic operations in MIPS require three operands. That's why I'm saying this is a rigid, organization. Okay, so we have 32 registers. Those registers I have already named it. Now let us see what are the instructions, possible instructions. Before I go to the instruction formatting, we must understand that what are the different types of instructions available. Okay, which are very common in MIPS fraternity. Okay, so I may not complete the whole list, but I'll show you some examples. This can be, you can get it from internet also, or you can get it from book also. So we have add. So instruction is here we will write instruction, then we will show some example. What is the meaning? And some comments. Let me add another one is here basically type. So add is obviously arithmetic type. Similarly, we have sub. Then we have add immediate. So what it supports? It supports. Example is we write add $S1, $S2, $S3. You know that what is the meaning of this one? $S1, $S2 plus $S3. So here comments key three register operands. All operands are in registers, 3 registers, 1, 2, 3. Similarly, you can have sub. The special instruction for add immediate is, this is called add immediate, ADDI. Here, one of the operands is a constant. Okay, so you can have something like this. So what it does? It is used to add constant. So these are 3 main arithmetic operations. I have not written subtraction example, you can write it here. Then data transfer we have. Data transfer has many things like load word LW, store word, then we have load half word. You do not need to load the full word, 32-bit word, you can load half word. Then load half unsigned word, load half unsigned word. Then store half word. Also you have load byte, then load byte unsigned, then store byte. Okay, and some more. There are a few more things. Now, usually we shall be comfortable with these two, load word and store word, because these are not required, very often. These are very important. Load and store, load word and store word. You load the whole word from the memory. Store word, you store the whole word from the register to the memory. So example is load word $S1 $20 $S2. Similarly, store word $S1 $20 $S2. So what is the meaning? Here actually $S1 equals to memory $S2 plus 20. Here actually meaning is memory $S2 plus 20 equals to $S1. So here from memory to register, here store means register to memory. Memory to register, register to memory. Load and store. That's it. These things are used for various types of loads and stores that may be required. But mostly we are done with this. So this one is data transfer category. Then we have logical category. Logical, we can have instructions like and, or, nor, then immediate. Or immediate. Then shift, left, logical, then shift, right, logical. This is basically, we call it SLL. This is called SRL. Like in 805, we have LLC, LRC, RRC, RAL, those instructions. And or are very simple. These are all again 3 operand instructions. You can understand why it will be 3 operand instructions, because and also requires 2 values. So example is $S1, $S2, $S3. You know that what it does. It does basically $S1 equals to $S2 and $S3 and so on and so forth. So if you know the convention, remembering won't be an issue. There are certain branch instructions which are also needed, like we have seen in case of 885, like jump instruction. So here also we have branch. So we can have branch, particularly conditional. So one is branch unequal. So we call it BEQ. So something like that. Example can be BEQ, say $S1, $S2, 25. Okay. So what does it mean? It means if dollar register 1 equals to register 2, then go to PC plus 4 plus 100. Go to this address. Now there is a reason for why it is PC plus 4 plus 100. So when this instruction is there, this needs to be understood clearly. Let me draw a picture here. Your branch instruction is here. BQ $S1 $S2 25, and this is the next. So let's assume that this is the program counter currently pointing to this. So I told you that whenever the program counter is executing one instruction, automatically it gets incremented by a value of 4, because this size is 4 bytes. Why? It's a 32-bit machine. So the next address is PC plus 4. Anyway, by default. So if it goes sequentially, after this, it should execute this instruction. Okay. Now what this instruction says that if S1 equals to X2, if S1 equals to, by the time you get to know that when the S1 equals to S2, the program counter has automatically incremented by 4. And there is an offset given 25. So it says that I would like to jump to 25th integer from now here onwards. So now you'll have to go to 1, 2, 3 up to 25th location, and each location is obviously 4 bytes. So that's why 25 into 4 equals to 100. Okay, so the address becomes 25 into 4. So these are all into 4 into 4 into 4. So this value will be PC plus 8. This value will be PC plus 4 plus 100. So if I write it, this is PC plus 4. This is PC plus 4 plus 4. This is PC plus 4 plus 8. This is PC plus 4 plus 12. This will be PC plus 4 plus 100. So 1, 2, 3, this is 25th element. Okay. So the address becomes PC plus 4 plus 100. So if you write an instruction like this, if your original intention is that if two register values S1 and S2 they are equal, you will go to this location. Then you can write this instruction. So your destination instruction should be now here. Whatever instruction you write. Okay. Similarly, I can write it branch on not equal. Branch on not equal. It's called BNE. It is the same. When the values are not equal, then you jump. There are other instructions also for comparing, so I'm not going to those instructions at this stage. Then unconditional thing. This is conditional. Unconditional. We have jump. So the instruction is J, only J. J2500. Then we have JR, jump register. Something like that. Then another one instruction is jump and link. This is jump register. Then it is jump and link. So you basically link to the return address. So this is JAL 2500. So what this does? This does go to directly to location 10,000. See, 2500 is the number of integers from the current location. So that's why every address is 4 byte. So 4 into 25, 10,000, 2500. This one is go to return address because this is a 32-bit register already. RA we have looked into it, so it will directly go. JL 2500. What it does? Return address is saved into a register. So you do this and then go to 1000. So what does it mean? You go, jump and link. You jump to this location, but before you jump, you save this address PC plus 4 into RA. So that after you do something, you can actually come back to the return address if needed. This is basically used for subroutine back. The effect, like if you would like to bring an effect of return, you should return to the location where from you are called. What happens in subroutine? When the subroutine is called, we go to that subroutine, finish it, and at the end we come back to the next location. So this is a kind of instruction which facilitates that. Jump 2500. So you go to the location 10,000, but before you go, what you do? You save the current value of the PC with PC plus 4, so that when you return, you get the return address here itself, RA in RA register. Okay. So that means you use this for calling a subroutine, and you use this for return from a subroutine. Up to this point, is it clear?
Sir,
Ah.
sir, we have to practice writing programs in this also.
Not now, but obviously I will give some assignments based on this. We will not be doing any simulation at this stage, but later stage I will tell you that what simulator is needed and how we'll have to write it. But it's better to get accustomed with the instruction set. In laboratory, you do not need to do the assignments based on MIPS, but you must know it because all the design will be based on this, whatever we will be designing in the circuit, we must know that what are the instructions. And obviously, the theory part where I will be discussing the architecture, internal architecture, we will be assuming that this instruction set is known to us. I told you this is instruction set architecture. First, we decide the instruction set, and then we go for designing the architecture. So that's why we need to know that what is the instruction set.
Okay, sir.
So up to this point, anyone if has any doubt, please let me know. This can be, you can find it in the book also as well as in tutorials. There are many available tutorials on MIPS. I have not completed the whole set, but you can complete it. So now if I write arithmetic in a high level code segment in C program, then possibly I'm talking about arithmetic instructions only. You can possibly convert them into assembly code. Like if I write A equals to B plus C, D equals to A minus E, you should be able to write the code. Okay. So can we do quickly something like that? So let's, all of you, just for a quick practice, if I give you an instruction something like this, so let's take this. F equals to G plus H minus I plus J. Assuming all variables are in memory, write the MIPS code for the above high level instruction. Do it. Let's say this is a C programming instruction, and I'm asking you to write a code. Do it. All of you, take your pen, paper, and write it.
Sir, when we do load word $S1 20 $S2, then 20 is byte, right?
Yes.
Okay, sir.
You can actually define the locations of f, g, h, I, j in memory first. The locations are based on your choice. I have no objection. You can declare a base register where and then an offset. 4, 8, 12 offsets for storing these variables. Anyone done? You can share your output. Okay, so I have received one solution. From Jagdish. He assumed that the values are stored in memory locations where the base location is there in S0. Okay, and with an offset 0 the first value, with an offset 4 the second value, and with an offset 8 the third value, and with an offset 12 the fourth value. Sushant has also given one solution.
The offset should be 1, right? Because it is in bytes.
No, offset will be here in bytes 0, 4, 8, 12. Okay.
Okay. Means that
2 bits is 4 bytes, that's why.
Okay. I got it.
Actually, it depends that how the assembly language assembler does it. Even if you write 1, 2, 3, that is fine. You'll have to tell that the assembler multiplies it by 4. So both the codes are fine, as logically they are correct. So if I share this one, so screen visible. Jagdish has given the solution. So he assumed that the base is at S0 register and 0 is the offset. So what he does, he brings the value from that location S0 plus 0, which stores F. Okay. Which stores F, or it should be GH. G plus H, I minus J. So how are you doing G plus H, Jagdish?
So I think I incremented, like I did wrong. I think F plus equal to G plus H I did.
Right. Anyway, so basically what it is doing, F plus G, H minus H plus I, huh? I think J equals to something
Yes,
like
sir.
that.
F equal to F plus the expression I did, I think.
Right. So you just modify that. Otherwise, logically it is correct. I mean to say that you're bringing the first argument, putting into T0, bringing the second argument, putting into T1, adding these two, putting into T0. Then you are bringing a third argument into T1. Okay. Then with which you are adding. Another load you'll have to do it now. There is something. This add y, it will come here. So I need to rearrange these instructions. Let me share my screen. Let me do it myself. So look into my video now. I'm now writing it. So I assume that this is my G location, this is H, this is I, this is J, this is F. Okay. So initially this one is $S0 plus 0. Okay. This is $S0 plus 4 and so on and so forth. So what you do, load what? T0 T1 both the variables are there. Now I can add so T0 is there. Now I will do load word $T1 $8 load word $T2 $12 then I need to do add $T1 $T2. Now I have one result is T1, another one is T0. Then I do sub $T1 T0 $T1. My result is in T1. So store word $T0. I think it will be $16 S0. This can be a code. I have reused a lot of registers. This is my one. So once this T0 T1's function is over, I am reusing the T1 here, T2 again. So there are many ways you can write the same code. This is S0 plus 8. This is S0 plus 12. This is S0 plus 16. So finally, S0 plus 16 is the result F. Is that clear to all of you?
Yes, sir.
Okay. Okay, so let's move ahead. So now you know that if one operand is in memory, okay, another is in register, what you will have to do? You will have to bring it from the memory. Okay, like if I write a statement like this, G equals to H plus A8. It's typical C statement. So when you declare an array, let's assume that A is an array of 100 words. And also let's assume that the compiler has associated the variables G and H with some registers S1 and S2. Here basically compiler has not associated, we brought the registers values directly to the registers, but you can always associate these values G and H with specific registers S0, S1, S2. I have not done that. That's a compiler level optimization. Okay. So you can actually now write down the code for something like that. Say if I declare an array of 100 words, okay, or 100 integers, okay, and I would like to add the 10th element or the 9th element of the array with one of any other variable, you know that how to write the code. So the address of this array element is sum of the base of the array A found in a particular register plus the number to select an element. So you need to know the base address which must be stored in a register, and then this element. So the you know that this one element is stored in one word, you'll have to multiply it by 4. Usually this multiplication is done at compiler level. You can directly write 8. Like I have used 0, 4, 8, 12. In MIPS books, you can see that these examples are like 0, 1, 2, 3, 4, something like that. So internally, it assumes that the offsets will be multiplied by 4. Okay. So what it requires a base address of the array. Because if I know the base address and from the index, I know that how many elements I need to skip to reach to this 8th element or 9th element. Okay, I can easily calculate it. These are all very simple calculations which can be decided at during the compilation time as well. So in actually in MIPS, words must start at addresses that are multiple of 4. So this is an alignment restriction. Okay, we don't start it with 3, 7, 6, and it should be multiplied by 4. Okay. And we have already looked into that why the little endian and big endian things are there. Okay, so those things are already I have discussed. So with this, we have probably understood that how to write simple codes for doing arithmetic calculations, assuming that the variables are either in array or in standalone variables stored in memory locations or stored in some registers. Okay, we can now do it. Also, we can use constants, adding constants. Like add immediate $3, $3, and 4. So what do you do? If you write an instruction like this, add immediate $S1, S2, 4. What it does, we know that register number S1 is equals to register number S2 plus 4. For 0, we have a 0 register which can be directly added. It is register number 0. Obviously, why there is a 0? Because see, if you would like to add 0, in many cases you may want to add 0 with something. Okay, so then it's actually a register, or you can say it's a temporary place where the 0 is stored permanently. It's like a fixed register where the value 0 is stored. So whenever you take that value, you automatically 0 comes. So that's the only reason. So now, what we understood from here, that if we would like to bring many values from the memory, obviously it will take time. So can someone tell me just guess it, that if you execute an instruction like this, let's say adding 2 register values this is one operation, and the second operation is adding 2 variables stored in memory. Both are addition. So can someone tell me that how computation time will change in both cases, and what will be the possible relation? Anyone, any guess? If you do not know the exact unit, whether it will be microsecond, millisecond, or nanosecond, you tell in terms of relative performance.
Adding 2 values stored in variables stored in memory, time will be greater.
Greater means what? I want some guess. Say you say that X amount of time is required to add 2 values in registers. How many times of X will be here?
$100.
Good guess. It's a good guess. Actually, it's more than 100. It's 1,000 times. Okay, the memory is very slow device. It's a slow device. So if it works, if the CPU works in the order of nanosecond, memory maybe works in the order of microsecond. Okay, so you can understand it's a order of 1000. Now that means to bring one value from memory to register using a load. During that time, you can actually execute thousands of instructions. So do you understand that this multiplication factor, even if it is 100 times also, it's too much. That just to load one value from memory to your register, during that time itself, if all your data is available within the registers, you can do 100 such instructions. And this is true. So if this is the observation, a technological limitation also, then what we shall do? What can be a solution? Any solution?
Using SSD.
SSD is a secondary storage device. SSD speed is not in the order of the registers. The speed at which internal registers work, they are fascinating speed. Okay. Actually, the only option is you increase the number of registers inside the processor. But again, that will lead to the cost increase in cost. If you cannot have so many registers inside the processor, because this will increase the cost of the processor. These registers internally, you require more space, you require more number of transistors, you require more circuitry. Essentially, the cost will be very high. Okay. So given the importance of registers, do you know what is the rate of increase in the number of registers in a chip over time? So if it is very fast, since they increase as fast as Moore's law, which predicts doubling the number of transistors on a chip every 18 months. Now that's the Moore's law, that the number of transistors in a chip of a unit area is increased, or it gets doubled within 18 months. In every 18 months, the number of transistors gets doubled, just doubled. So this is a fast approach, and there is also a slow approach. Since programs are usually distributed in language of the computer, so there is obviously an inertia in instruction set architecture. Okay. So the number of registers increases only as fast as new instruction set become viable. Registers are needed when you increase new instructions. So when your instruction set changes, so that usually it's not that fast. Instruction set is a slow one, because if you change the instruction set, what you'll have to do? You'll have to change the entire compilation process. The whole software architecture needs to be changed. So that's why you don't find these days registers, number of registers are changing too fast. They're almost freezed or constant. Even though MIPS registers, we assume that 32-bit wide, So there is also a 64-bit version of MIPS. So you can have MIPS 32, MIPS 32 and MIPS 64. Both contains 32 registers, but here the registers are 64-bit, here 32-bit. That's it. And obviously, because they are multiples of 4s and 8s, you can see that they are very good in the context of current programming. We have integers, floating point, double precision floating points, which can easily fit into these locations. That's one advantage. Now, instruction encoding I have not talked about yet. Instruction encoding is one important. I mean to say that we are talking about instructions, but how these instructions are encoded, that I shall discuss in next class, which becomes the basis of designing the hardware. Now, if this is my instruction, which is obviously 32-bit. I know that this is 32-bit. So how do I divide this 32-bit into various segments? That is, we should learn. This is instruction formatting. Every architecture has its own format. See, essentially, whether we write add or add immediate, sub or not, and they are binary codes. And these binary codes must be written here itself. There is no meaning of this in computer language. It's only a 32-bit number. And that 32-bit number is a mapping of this particular high-level representation, like add I. But computer hardware is more interested with those binary numbers. That's called encoding the instructions. Because your hardware will only understand those encoded instructions. They will not understand this. This is for our purpose. Because we are not comfortable in seeing these numbers 0, 1, 1, 0, 1, 0, 1, 0 up to 32-bit. So we gave them some meaningful name. Okay. Is it clear, all of you? And I also expect you please recap your knowledge on digital logic, like particularly binary representation, 2's complement, 1's complement, signed extension. Those things are trivial things. You should remember. I do not want to repeat those things because we have a lot of things to cover. So please, I recap those things. Simple binary numbers, hexadecimal numbers, 1's complement, 2's complement, signed representation, signed magnitude representations, all these things. These are basic things. One's complement, 2's complement, these are standard things, and you must recap those things. I shall come back to the assembly part later stage when we will be writing more complex programs. But at present, I'll stop for discussing the assembly part, we will switch to the hardware part. So before I actually go to the processor designing, I must assess your state, that how you are placed in, because the next part will be the basic processing unit, designing of the architecture. So are you ready to, take, I mean to say, the move to the designing of the central processing unit, CPU or basic processing unit? Anyone, if you have any doubt up to this position, please let me know. Because the vehicle will move very fast now. Next topic is the heart of this course. Fine.
Yes.
So in that case, let me start this. Or shall I skip the designing, CPU designing part today, or we'll start afresh from the next class? What is your suggestion?
From the next class.
Okay. Yeah, that's a new one. So then let's have a discussion. Whatever you have, anything, if you have anything to discuss, we can now discuss based on theory, lab.
Sir.
So I expect that you will recap your knowledge on digital electronics, particularly the binary arithmetic part. Even though when in the CPU designing part, we have a full chapter on designing the arithmetic logic unit, but those are circuit designing for the arithmetic and logic unit. So you don't expect that I will tell you that how to do addition of binary numbers, how to do subtraction of binary numbers. I expect that those things you have already done it. Okay, that's what I'm saying. So number representations, binary, hexadecimal, ones complement, twos complement, how to do addition, subtraction. Okay, all these things you please recap. Those
So
things are
like
needed.
adder circuits, full adder, right?
Full adder circuits are basic. I hope that you remember those circuits. Even though you don't remember, I will introduce those circuits. Okay, the basic units I will introduce, but it's obviously I will not go into the spending more time in designing full adder circuit. Rather, we will design advanced level adders and faster circuits. And also the sequential part, particularly the counters and registers. So please look into the designing of counters and registers, synchronous counters, asynchronous counters, parallel in registers, parallel out, parallel in, serial in, serial out, serial in, parallel out, these registers, multiplexers. Multiplexers are very important because in our design we need to take the help of multiplexers in the whole data path. There are possibly, other than the registers, multiplexers are the busiest unit inside a processor. Everywhere you will find multiplexers. It's needed because there are multiple paths coming. You can understand why do we require multiplexer? We require multiplexers when there are multiple inputs coming and one of them to be selected. So multiplexer, concept of multiplexer is very important. Even though it is very simple in terms of digital electronics, it is very simple, but still probably you have only used the input lines as single input line multiplexers, but here we may be using the input lines will be multiple bits. It's not a single bit. Okay. Even though in the simulator environment for hardware designing, Logisim, we know that those multiplexers are available, but understanding how those multiplexers work is very important. Otherwise, the timing, you will not be able to generate the right timing. CPU is a sequential circuit. Everything is based on clock pulse. It's not like that it's randomly doing. It's based on the clock pulse. So timing is very important. Explicitly, we need to mention that at what time what register will be open, at what time what register will be closed. One day I was talking, if you remember, I gave in the first lecture itself. Let me open up this first lecture where I was describing that, if you remember, let me open. Yes, something like that. You see a conceptual diagram of the CPU. Now these are the units. There is a common bus. So when the data is available at the output gate of ALU after the arithmetic operation, this value should not go to anywhere. If it goes to one of the GPRs, you know that that particular GPR input gate should be ready and others input gate should be closed. So timing is very important here. And while this transfer is going on, since this is a common path, this may not be a common path also if the design is done in a different way, but at present it's a common path. You must ensure that all other gates are closed. And when do you ensure the gates are closed? Depending on the time. So the timing is very important. This diagram looks very simple from outside, but whenever we need synchronous transfer from here to here or here to here or here to here, we require time. So that's why concept of sequential circuit designing is extremely important. Though we have a systematic approach to learn how to design the processor, so don't worry. I'm pretty confident by the by the end of this course you shall be able to design your own processor. So we need to learn the method. So that is what we are going to do. Okay.
Sir, I had a doubt in the OS lab assignment.
Follow. Get out.
Sir, can you tell the format in which relative commands are given via relative and absolute paths?
Relative and absolute path. Relative and absolute path means you are talking about, say for example, you have a file. Okay. So in the current, from your current directory, okay, if you would like to access anything within the current directory, so that is because that is directly available. Now whenever you would like to access something which is outside your directory, then that becomes, there is a relative path. Okay, say let me take an example. Or shall I open it? This AnyDesk. Yeah, let me see that AnyDesk is open or not. Yeah, AnyDesk is open. Yeah. Are you able to see my screen? AnyDesk screen?
Yes, sir.
Now say if I run a command ls, okay, so what it shows? It basically shows all the files into my current directory. Got it? So if I go to a directory above, now these are the files which are, what is my present working directory? /home/server_admin. This is my current working directory. Now if I do an ls, it will show the files which are files and directories which are under the server_admin. Okay, but if I'd like to see all the files which are in a different directory, so what I can do, say for example, I would like to see all the files and directories that are under, say, OS lab. Oh. If I write like this, you see what it is showing? It is showing all the files which are under OS lab_2021. It's not showing the files in my present working directory. My present working directory is this. If I do write simple ls, so it's giving the list of files which are in the current working directory. Now if I go to a relative location from the current location, I can also see the files. That is what I did it. Quest lab. This is a kind of relative.
So suppose we have to execute that XYX from here only.
Do it, no problem. So if you would like to, if you want to execute this one, now, what you can do, do it. So now the path is relative. XYZ is a binary file which is under this. Okay. Hello world. I think this was a infinite loop, no? Got it?
So this thing we have to implement in that, right? Or can we use system call directly?
No, this thing you'll have to implement. This thing you'll have to implement.
Okay.
Any file you can execute it from anywhere. So the path, absolute path you can give it. So this is the absolute path. See, there are many ways. This is what the path I am currently, if you look into this one, this is not the absolute path. This is the relative path with respect to my current directory. Okay. Now, if you would like to know the absolute path is obviously something like this. You can always give an absolute path like this. What is the absolute path of XYZ? It will be root. I think, let me see that what. Path should be home slash, yes, it should be home slash something like dot slash home home is not there, so basically so I'll come one out, then one out, okay. I think it will be under which directory this is. Okay, so this is dot slash where is home. So this is root. Okay. Now if I do it /home /home, then server admin, then lab, then XYZ. This is running. So this is the absolute path of the file. Under root, this is the root directory. Under root there is a home directory. Under home there is a server admin directory, and then this one. Correct. So cd home, then server admin. Now my present working directory is this. Now it is coming. Sorry, I was doing wrong thing. So now this is the absolute path. Server admin, then OS lab, then we are in XYZ. Now look into this. This way also the code is running. Now decode this part. So what is my present working directory? My present working directory is under home and server admin. What I am doing? My present working directory is here. I am moving one directory up. So it goes to home. I am moving one directory up. It goes to root. Okay. From root, I am going to the home again. I am going to the server admin again. Then I am going to the OS lab again. And then I am going to the XYZ. So this is the absolute path of XYZ from my current position. Okay.
Sir, and in that terminal which we are going to implement, only executables will be executed, right? And the built-in commands.
Yes, executables and built-in commands. Executable means if you write your own code, okay, you make an executable file that should also run.
Means we should also think like we should be able to compile that file from there on.
No, compile means what? See, GCC is, are you talking about executables like GCC?
Yes, sir.
Yeah, GCC is a executable which will run. GCC is a command.
So that will.
See, GCC is not an internal command. Okay. So shell in, for commands like cd. Okay. Where basically you can use the help of executing internal commands like cd ls, because these implementing cd ls will take long time. It's very difficult to implement them from the scratch. So you can take the help of executing these commands, and their responses you just print it, redirect it. Okay. Whereas GCC, even if it is already executable is already available, okay, it varies from computer to computer. Okay, so it's a separate program. GCC is not part of the operating system. So built-in command means those which are like pwd, okay, then ls, then cd. These commands are already implemented, so you can actually execute them and take their responses.
Like sir, from our terminal, we should be able to like compile our programs.
Yes,
Okay.
because
So
compile our programs means you will be using GCC. Okay,
okay. Means any executable we should be able to execute, right?
right. Any executable you should be able to execute. Like for built-in commands, you do not need to give, command like this. You just write CD, na? Whereas in your program, you need to give a, options like this, dot slash. Dot slash tells that this is a binary file you are going to execute. This is your command. Okay. To execute binary files which are created by the user, you require dot slash. Okay. So they should be running, they should be executed in a different mode than to execute CD. Okay. So let's see that what the outputs are coming. Okay, I would like to see that assignments how you are submitting. Don't worry about whether you are able to implement all the functions or not. Try to implement as much as possible and we'll see.
Okay, sir.
So can you extend the deadline for this project then?
Extend. Let me see the responses. If I think that many people are not able to submit, I will extend. Okay. It's given till Sunday night. Huh? I think Sunday night, na? If I remember correctly, it was given
Yes.
Sunday night. Wednesday, Thursday, Friday, Saturday, 5 days. What is the problem?
So we
Try it.
have internship then.
Internship interviews. What?
Yes, sir. Preparation.
That's fine. Okay, you see that if I find that if I feel that it needs extension, I will extend it. Maybe 3-4 days extension, I will do it.
Okay, sir.
Okay. So anything else? So next class I shall be starting the CPU designing. So don't miss it from those class onwards. It will be a little bit what I will say interesting also. So please be on time and try not to miss those classes because these concepts are very important while you will be designing the circuits in lab. And also overall knowledge gaining will be much better. That's it then. Thank you for today.